Hello, this is the final presentation for the Breaker Energy Automation and Management System project, also known as BEAM.
Here's the team behind BEAM. Tristan Palumbo, Electrical Engineering. Anika Zheng, Electrical Engineering. Nicolas Rubio, Computer Engineer. And myself, Hugo Tarira, Electrical Engineering.
On February 15, 2021, Texas experienced record low temperatures, leading to increased power demand from heating and multiple power plant failures. As demand exceeded supply, grid frequency dropped below 59.4 Hz, forcing grid operators to start rolling blackouts. That is just one example of the importance of grid stability. The transition to renewable energy and battery-supported grids can also impact grid stability. This is why we propose BEAM, inspired by our sponsors, Professor Sun, Professor Tian, and the previous grid stabilizing frequency detector project. BEAM is an affordable attachable motorized unit for existing breaker panels with grid frequency detection. BEAM automatically sheds non-essential loads when grid frequency drops below 59.4 Hz, preventing total blackouts while keeping essential appliances running. BEAM also has energy management features and allow consumers to turn off appliances at home remotely for home efficiency.
Goals and objectives. The goals for BEAM are to enable remote control of the circuit breaker switches via secure user-friendly interface, detect frequency drops in the power grid and automatically switch off breakers to protect appliances, enhance energy efficiency by turning off high-consumption devices like water heaters and air conditioners, ensuring easy installation with a compact, reliable, and mountable design. The key objectives are to design a secure remote access system for user control, to integrate sensors to detect frequency drops and trigger automatic responses, create a compact, low-complexity device that uses minimal wiring and durable mounting solutions, incorporate high-quality components for reliable performance. The stretch goals are to have global remote access using cloud-based communication, adaptability to different breaker panel types, and add advanced features like switch state detection.
Engineering requirements and specifications. We have three main requirements for our project. Accurate positioning to designated switch with a 5% error, frequency detection accuracy with a 1% error, and max response time for each switch with 20 seconds. We also have some secondary requirements that you can read here.
BEAM's system consists of three parts: the stepper and DC motors attached to the breaker panel, the motor unit PCB and battery pack inside of its housing, and the frequency detection unit PCB. In this presentation, we'll refer to the motors, its PCB, and the batteries as the motor unit, and then the frequency detection unit as a separate part of the system.
Here is a hardware diagram for the main motor unit. As you can see, we have a 15-volt rechargeable battery that is connected to three step-down regulators. The first 10-volt regulator is connected to the Y-axis motor circuit, the second 10-volt regulator is connected to the X-axis motor circuit, and the final 3.3-volt regulator is connected to the MCU. The MCU itself sends signals to the motor drivers depending upon the mobile device's input or the frequency detection unit's input. Here's the hardware diagram for the frequency detection unit. We step down the voltage using a power transformer, and from that step down voltage, we take it to a frequency sensor that gives us the frequency data to the MCU. Then from that step down voltage, we use an AC to DC circuit and a step down regulator to be able to power the MCU.
The mechanical system for BEAM is shown on the right. It consists of a mini DC linear actuator which enables the circuit breaker to be turned on or off. This is mounted to the linear guided stepper motor, which moves the actuator to different circuit breakers. The system will be mounted onto a blank side of a breaker panel or wall with enough distance so that it's still able to change the state of the circuit breakers. For the main unit of BEAM to work, at least two of the motors must be used to move to different circuit breakers and to change the state of each of those breakers. Each motor is ranked by a point system from 1 to 5 on the right. The motors compared are the brushed DC motor, the brushless DC motor, the stepper motor, and the servo motor. For the motor responsible of the horizontal axis of BEAM, torque at low speed, inexpensiveness, compatibility with controllers, and power consumption are the specifications looked at. For the vertical axis motion of BEAM, precision, efficiency, speed control, Durability and maintenance and long lifespan are looked at. To appeal to the market, beam must be easily mountable, have a simple design, and be easily controlled. Because of this, the motors chosen are the DC brush motor and the stepper motor, as seen in the table. Below I have two charts, one for the stepper motor driver and the other for the DC motor driver. The specifications include the logical voltage, the drive voltage, the logical current, driving current, the quantity, and the price. The stepper motor driver table compares the L298N, the A4988, the TMC2209, and the DRV8825. The DC motor driver table compares the L298N, DRV8833, and the TB6612. The sizing for all of the drivers are similar with the exception of the L298M, which is too large for this application. Although the TMC2209 has a silent stepping mechanism, the 8825 is much easier to use with a higher power application. For the DC motor, the DRV8833 has more built-in protection than the TB66. The DRV8825 is a TI chip, it has a wide voltage range, and it has a good efficiency. The DRV8833 is also a TI chip, but it's small and it has a simplistic design.
For our wire communications, we had a choice between UART, I2C, and SPI. We chose UART since it's the least complex protocol and it uses the least number of wires. Between USB to serial, we decided to use the CP2102 due to its low current draw.
For our wireless communication, the two main options we considered were Wi-Fi and Bluetooth, and ultimately we decided to go with Wi-Fi for a few reasons. For one, Wi-Fi generally has longer range than Bluetooth, and since our system is in a household, we want to ensure that the user will be able to connect to their system from anywhere within their home. Wi-Fi also has higher connection capacity and higher transfer speeds, and for us, reducing latency is one of our utmost concerns. And Wi-Fi also has good interoperability. So in general, Wi-Fi we felt was the best choice for our project. So for our MCU selection, we went through a variety of different MCU models to really find the best MCU that fit the needs of our project. And ultimately, we settled on the ESP32 as our choice for our MCU. We did this for one because it was the most affordable option that we could find that still provided sufficient processing power for our project. The ESP32 has relatively low power consumption, it has sufficient GPIO pins that our project needs, and it also has all the desired wireless communication modules that we wanted in our MCU.
Power distribution table for beams motor unit. This table represents the worst case scenario power usage for each component in the main motor unit board. Battery technology selection. For our rechargeable battery, we decided to research into lead acid, nickel metal hydride, lithium ion, and LiPo batteries. Since we were looking for the highest energy density, we settled on lithium ion and LiPo, tipping the scales towards lithium ion since they are safer. From the many different lithium ion batteries we could choose, we decided to use the Samsung 30QP since it has a good nominal capacity, a good continuous discharge rating, and it comes with general protections. Motor unit regulator selection. For the motor unit, we require at least two voltages, 10 volts and 3.3 volts, and both of them have to come down from the battery voltage, which is 12 to 17 volts. We researched three different regulator technologies, linear, buck boost, and flyback regulators. Between these three, we decided to use buck regulators because of their high efficiency and moderate size, especially compared to flybacks. Within buck regulators, we researched the LT1377, the LT1172, the ADP5073, the LTC7149, and the LM2596. We decided to use the LM2596 largely because it's reliable and common. It also has an inverter output and it has a high current rating of 3 amps. Frequency detection unit regulator selection. The regulation required for the frequency detection unit goes from 6.5 volts to 3.3 volts. We researched three different technologies for this section as well, linear, buck boost, and flyback. Between these three, we decided to go with linear technologies, mainly because they're simple, small footprint, and they're typically used for low current applications. As for specific linear regulators, we looked into the LM317, the AMS1117, the L7805, the LT3080, and the NCP1700. Between all of these, we decided to use the AMS1117. simply because it's compact, low cost and simple, and is widely available.
For our power transformer, we first ruled out core and planar transformer type, because core type transformers are typically used in high voltage, high power applications like substations and industrial factories, and planar transformers are designed for high frequency applications while the power grid operates at 60 Hz. After narrowing it down, we chose the VTX transformer, which is a shell type transformer. It's more affordable and readily available compared to toroidal transformers. Compared to the TCT3 transformer, the VTX transformer allows us to configure the secondary voltage in series or parallel. This flexibility gives us more options when deciding how to rectify AC to DC. The first thing we need to consider when choosing a rectification method is that the secondary side of the transformer must share the same ground reference as the MCU. This is so we can obtain an accurate frequency measurement from the MCU for the frequency sensor. If we use a bridge rectifier, the secondary side of the transformer wouldn't have the same ground as the MCU. To fix that, we need an op-amp to measure the voltage difference between the transformer terminals and then feed it to the MCU. Therefore, we ruled out bridge rectifiers and MOSFET bridge rectifiers. This is not only for the sake of simplicity, but also using half-wave or full-wave center tap rectifiers instead of a full bridge helps reduce voltage drop from 2 diodes down to just 1. Comparing all 3 parts from the table, we settle on SPT because it has 2 built-in Schottky diodes, which allow us to do both half-wave and a full-wave center tap rectification, and it is more readily available. To detect the frequency of the grid, we need an analog signal processing method. We decided to use DC bias and scaling. Compared to methods like zero crossing detection and frequency to voltage conversion, this approach gives us access to the raw signal, which offers more flexibility in the code. It only requires a simple voltage divider and a DC bias circuit, which are just basic resistors and capacitors. Since these components are straightforward and widely available, we don't need to do any in-depth part selection for this part of the project.
Here we have the main motor unit schematic with 5 major sections to cover. First, we have the motor driver section that includes the X and Y axis motor drivers input, output, power, and power control connections. Next, we have the external regulator section that includes the input battery connector, as well as input and output connectors for each regulator, as well as power controls for each of the 10-volt regulators. Next is the under voltage lockout section, which includes the UBLO circuit that comes from the LM2596 datasheet that is connected to a logic level shifter that goes from 10 volts to about 3.3 volts that feeds to the input on the ESP32. Next is the USB to UART bridge, which is mainly copied from other ESP32 dev kits with some minor tweaks for improved reliability. Last, we have ESP32 module connections, which largely come from ESP32 dev kits.
As mentioned before, the DRV8825 and 8833 are both TI motor drivers. These TI chips are normally preferred because of their reliability and detailed datasheets. This makes constructing the schematic and the board a lot easier due to the large amount of information on their datasheets.
Here we have the regulator breakout board schematic for the 10 volt switching regulator, the 3.3 volt switching regulator, and the 3.3 volt linear regulator.
Here we have the schematic of the frequency detection unit. Starting with the top left, we have wires coming out of the outlet. The fuse and MOV are there for surge protection. Then we have the transformer and AC to DC rectification with a full wave center tap configuration. At the end, we have our 3.3 volt regulator as a breakout board empowering the MCU with ESD protection. Lastly, we have our DC bias circuit for frequency sensing with an ADC input to the MCU for Fourier transform.
Here's the main motor unit PCB with all major components highlighted. For this board, we decided to use 2 10 volt regulators instead of 1 due to increased efficiency at lower current.
These are the DRV8825 and 8833 breakout board PCBs and were made to swap out the motor drivers in case they burnt out during the project.
Here is the PCB for the 10 volt switching regulator, the 3.3 volt switching regulator, and the 3.3 volt linear regulator.
The frequency detection unit PCB is 4 layers. On the far bottom left, we have the cable from the outlet connecting to the primary side of the power transformer, stepping down 120 volt to 4.5 volt RMS, or around 6.4 volt peak. This is followed by AC to DC rectification in a full wave center type configuration in the bottom right. We also have our 3.3 volt regulator to power the ESP32. Lastly, we have a voltage divider and DC bias circuit connected to the ADC input of the ESP32 to obtain a properly scaled sine wave voltage from the secondary side of the transformer for Fourier transform processing, which is used to determine the frequency of the grid. Shown here is an example of what the data looks like inside the frequency detection unit. On the left is the raw sample of the 60 Hz sine wave. It looks triangular because the sampling rate is 240 samples per second, which means there are 4 samples for every 1 period. On the right is the Fourier transform of the captured data. It tells us the frequency of the signal, which is 60 Hz.
So looking at the high-level software workflow of our project, we first start with initializing the breaker states in the code to match the breaker states that are of the physical breaker. And from there, the main MCU will await an input from either the mobile app or the frequency detector. When a command from either of those is received, we first analyze that command to see if the desired breaker is already in the position that we're commanding. Essentially, is that command redundant or not? If so, we'll throw the command away and we'll turn to the MCU awaiting input state. Otherwise, we'll proceed with the command to turn on the motors to flip the breaker to the desired position. While that's going on, we'll implement a wait in the code to make sure that nothing else happens while the command is being carried out. And then once the command's finished, we'll update those breaker states in the code to match what the breakers are physically and return to the MCU awaiting input state. So breaking down the software workflows a little further, we have 2 main initiated software workflows in our project. One automatic workflow from the grid frequency detector and another user-initiated workflow from the mobile app. Looking at the automatic frequency detector workflow, we can see that it starts with a spike in the grid frequency and the ESP32 detecting that. It'll create and format a command to send over Wi-Fi to the main ESP32, which will receive and parse that message and then command the motor driver to flip the appropriate breaker. And looking at the user-initiated software workflow, it starts with a user input from the mobile app. That message will be formatted and sent also over Wi-Fi to the main ESP32, which will parse and verify that message, and then command the motor driver to flip the appropriate breaker. And now here, it's important to note that this ESP32 will then send a return message back to the mobile app to update the status in the app of the breaker. So for developing our mobile app, we went through a variety of different choices for tools to use, and ultimately we settled on using Flutter, which is a framework developed by Google for making mobile apps that uses the programming language Dart. Flutter has a lot of great qualities. For one, it has cross-platform support, meaning that our app will be able to run on both iOS and Android devices. It has a lot of quick development features, such as hot reloading, which allows you to see changes quickly in your project without having to rebuild the entire thing. And Flutter is also equipped with a very versatile widget toolbox, which widgets are anything from menu bars, drop downs, buttons, switch buttons, anything you can really think of is a widget, and those are already integrated into the framework for the developer to use to speed up and simplify development. So for the design of our mobile app, we broke our app up into 3 main pages, with each page having a designated functionality. This is the control page, which is the main control panel where the user is going to be able to control the different breakers. At the top, you can see we have the page title. In the center is the breaker control area where the user will actually be flipping breakers. At the bottom, we have a notification bar that pops up for roughly 2 seconds whenever an event occurs. And at the very bottom, we have the page menu bar where the user is actually going to be able to navigate between the different pages. So like I said, here is the breaker control page where for each breaker tile, we have the current status of the breaker and a switch button on the right that allows the user to actually send a command to flip a breaker to a desired position. So for our next page, we have the system page, and the purpose of this page is to display useful in-depth system information to the user. We display 3 key pieces of information here, being the grid frequency, the Wi-Fi connection status, and the battery status. The grid frequency will show the currently measured grid frequency from the frequency detection unit, which is updated in real time. The Wi-Fi connection status will show whether or not the app is connected to the hardware of the system, and the battery status will show whether or not the battery is charged or dead. For our final page, we have the settings page, which allows the user to configure the automatic frequency response of the system. Here, for every breaker, there is a checkbox that the user can select to save a certain frequency response to the hardware. When those settings are saved to the hardware whenever your automatic frequency drop occurs, these settings will be referred to carry out the automatic frequency response.
In performing the motor unit testing, we kept several things in mind, such as making sure the linear guided stepper motor can transmit the actuator to its desired circuit breaker position, and the DC linear actuator can actually switch the breakers. On the right, we could see the video of the operation, and we also performed multiple tests on the voltage regulators to ensure that it properly stepped down the voltage with minimal power dissipation and heat generation.
Shown here are our frequency detection results. On the left, the table displays the frequency input simulated by the signal generator, and the frequency output displayed on the app. The results are well within 1% error. On the right are a few images highlighting our testing process.
These are a list of problems that we've encountered during the testing stage of Beam. The first two are the regulator overheating, motor driving PCB sizing, and connection errors for the drivers. To solve this, space was added for a large heatsink on the regulator board, and multiple revisions of the main PCB were made. When testing, we also tried to find app malfunctions to then debug them to enhance the user interface. Lastly, there were issues with the attachment for the linear actuator, and to solve it, we redesigned it through trial and error. Stretch goals we would solve include the ability to determine the state of a switch if someone flips the breaker physically and through the app at the same time, be able to tell the user when to charge the batteries, and finally add login security to prevent others from misusing your automated breaker. This is the cost breakdown for our project, and as you can see here, we have the pricing for the motors, batteries, and charger, components for the 2 times we prototype with the development boards, the ESP32 development kit, PCBs and their components, the actual circuit breakers and the panel, miscellaneous items that are included on the right, and the PVC housing for the motor unit. This brings the total price of the project to $1,226. For this project, we split the work into 4 different ways. Anika was working on all of the frequency detection and the unit for Beam. Hugo was working on the rechargeable battery, the main motor PCB, and the voltage regulators. I was working on the motor design, the motor driver design, and the mechanical design, as well as the motor code. And Nick was working on the mobile app, Wi-Fi integration, software design and implementation, and all of us were working on the MCU selection and implementation.